Hello everyone, this is Amit. I welcome you all in the video lecture series of the subject Operation Research. This is our 7th lecture related to the chapter Transportation Problem, in which we will study about degeneracy in transportation problem. So let us begin our discussion. What is degeneracy? You might have a question, what is degeneracy? So let us begin our discussion. Before we move forward towards an example, first of all, let us try to understand what is degeneracy. So, degeneracy is nothing but when you obtain the basic feasible solution of a given transportation problem. So, at that time, if the number of allocations that you are having is less than m plus n minus 1, then the problem is said to have a degeneracy. So, you cannot obtain the optimal solution for that. So, to obtain the optimal solution, what are the steps one needs to take to attain the optimal solution or to reach the optimal solution? So, how degeneracy is removed in the transportation problem, that we will see with the help of one example. But degeneracy is nothing but if the number of allocations that you have obtained that is less than m plus n minus 1, then one can say that there is a degeneracy in the transportation problem, and that must be removed to obtain the optimal solution. So how to remove that, that we will understand with the help of one example. So example is given here. There are 3 manufacturing plants X, Y and Z with capacities 80, 50 and 90, which supply to the distributors located at A, B, C and D and E with requirements of 40, 40, 50, 40 and 80 units. Unit transportation costs are given below in rupees. So this table is given to you in data, and those supply capacities and requirements of distributors are given. So there are 3 manufacturing plants, namely X, Y and Z. Its capacity is given at the end of each row, that is 80 for X plant, 50 for Y plant and 90 for Z plant. There are 5 distributors where the requirement is there. So the requirement of each distributors A, B, C, D and E, its requirement is given at the end of each column. So for A it is 40, for B it is 40, for C it is 50, for D it is 40 and for E it is 80. So this is the data that is given to you. Now let us check what happens. So the very first step that we had studied, that is checking whether the problem is a balanced or unbalanced problem. So let us check. So if you make an addition of the supply capacities as well as requirements, then one can find that this is an unbalanced problem, because if you do the addition of these capacities of all the 3 factories or all the 3 manufacturing plants, 80 plus 50, that is 130, 130 plus 90, so it is 210. Similarly, the requirement is 40, 40, so 40 plus 40, 80, 80 plus 50, it is 130, 130 plus 40, it is 170, and plus 80 is 250. So the requirement is 250 and the capacity is 210. So we can say that this problem is an unbalanced problem. So to obtain the solution, our main thing we should do is to balance the problem, then and then only we will get the basic feasible solution, because basic feasible solution is always obtained for the balanced transportation problem. So our first task will be to balance the given problem. So balancing by adding the dummy row with capacity of 30. So and using warm method to obtain the basic feasible solution. So moving to our next slide. This is initial basic feasible solution that is obtained with the help of warm method. I have not written the steps how this allocation is obtained, but with the help of warm method that we had already discussed in our previous lectures. So how to use Vogel's approximation method to obtain the basic feasible solution. So I have directly written the final step where you can get the allocations accordingly. So this is the final, we have added the dummy row whose old unit cost is 0 and with capacity of 30. So now you can see the problem is balanced, and after balancing the problem we had applied, or we had used warm method to obtain the initial basic feasible solution. So with the help of warm method we have obtained this type of solution. So the total capacities is also exhausted, and then after we had got this final solution. So now you can see the total number of allocations: 1, 2, 3, 4, 5 and 6. So we have got we have got 6 1, 2, 3, 4, 5, 6 and 7. We have got 7 allocations. Here it is allocation of 50 and 30, so it satisfies the capacity, that is 80. Here it is 40 and 10, so it is satisfied 50. Here 40 and 50, so 90. Here it is 30, that is as it is. Here it is 40 in the column. Here it is also 40. Here it is 50. Here it is 40. Here it is 80. So everything is satisfied, and we had got the final solution using warm method. So the total number of allocation is 1, 2, 3, 4, 5, 6 and 7. So now let us check whether we are having any degeneracy in our this given transportation problem or not. So according to the formula, m plus n minus 1, m stands for number of rows and n stands for number of columns. So the number of rows are 4 and number of columns are 5. So 4 plus 5 minus 1. So 4 plus 5 is 9. 9 minus 1, that is 8. But the allocations that we had obtained using warm method is 7. So now you can say that there is a degeneracy in the given transportation problem. So degeneracy is nothing but if it is less than m plus n minus 1, if the allocations that you had obtained using the any method, whether northwest corner method, least cost method or warm method, if the allocation is less than m plus n minus 1, then one can say that there is a degeneracy in the given transportation problem, and that must be removed. So what are the steps so that we can remove the degeneracy? So obtained allocation is 7, so there degeneracy at the initial solution, so we cannot test for optimality straightforward. Yes, so first task will be to remove the degeneracy, and then only we will go for the optimality test using Modi method. So now considering any one cell with least cost as occupied cell and put the value epsilon in that cell. So now what we will do, there are many unoccupied cells, means unoccupied cells are those in which we are having no allocation. So we will consider one cell such as an occupied cell. We will consider any one cell out of the unoccupied cell as an occupied cell, and then we will see how the degeneracy can be removed. So now considering any one cell with the lowest cost as occupied cell and put the value epsilon in that cell. Now epsilon is a very small value, it does not affect the final solution. It's very small, point value 0.001, or it is very less, so it does not affect the final solution answer. So moving to the next step. So in the least cost, see, out of this whole table the least cost is over here, here, here and here. So now you might have a question, where to put that epsilon value such that it can be considered as an occupied cell. So if you put that epsilon value should be put in that cell where the loop formation or that particular cell should be independent. Substitute the value of epsilon in such cell such that there should not be any loop formation. It should be independent cell. There and there only you will have to substitute that smallest value epsilon. So in the whole table you can see the least or the lowest cost is in this row, dummy row. Here it is 0, here it is 0, here. So now you might have a question, where to substitute that epsilon. So epsilon is substituted in a such cell such that that cell is independent. Independent cell means from that there is no loop formation. If I substitute epsilon over here then and consider this as an occupied cell, so what is the procedure to draw the closed loop? Closed loop should be drawn such a way that its starting point and end point should be same. You can draw the loop with the help of horizontal and vertical lines such that its starting point and ending point remain same. So if I substitute epsilon over here, then you can see I can draw the vertical line. Then as per the rules, to draw the loop you can take and right hand turn from the occupied cell only. So if I have considered substituting epsilon over here and I am drawing the vertical line, then I can take turn from here. I can extend till this, because turn can only be taken from the occupied cell. So again it can be moved right hand turn, again it can be moved right hand, and again it is reached to the starting point. So here the loop formation takes place. So you cannot substitute epsilon over here, because that cell should be independent where the loop cannot be formed. Now you can substitute over here also, over here also, or over here also. So I have substituted the epsilon in this particular cell. Now you can check, if I am drawing the loop, I cannot reach this point, the same starting point. If I have substituted epsilon over here, now if I am drawing this vertical line, then I can take turn from here, I can extend up to here, and I can again take down, but here there is no occupied cell. So a right angle turn can only be taken from the occupied cell only. So here the loop, closed loop, is not formed. That's why I have substituted epsilon over here. You can substitute over here also. Here also the loop is not formed, but that again depends on your personal judgment. Now using worm method, using Modi method, not worm method. Now using Modi method, I have obtained the values of ui, that is there are 4 rows, so u1, u2, u3 and u4. Similarly for column, that is v1, v2, v3, v4 and v5. So we have obtained using the relationship for the occupied cell, that is Cij is equal to ui plus vj, giving this as an equation x. Now all the occupied cell, for all the occupied cell we are finding this C13 U11, sorry C13, this is an occupied cell, U1 plus V3 is equal to 6. So we had obtained all the equations that we had seen in the earlier method of Modi method. So same steps are followed. So all those values of U1, U2 which we have obtained over here, that I have substituted in this main table. U1 we have assumed as 0, then we can obtain another value by substituting any value is equal to 0. I have substituted u1 is equal to 0. You can take any value is equal to 0, such that you can obtain all the other values. So I have obtained u1, u2, u3, u4, v1, v2, v3, v4 from these equations, and I have substituted in this. Now finding out the opportunity cost for all the unoccupied cell. So for that the relationship is delta is equal to the relation is delta ij is equal to Cij minus ui plus vj. So the unoccupied cells are those in which there is no allocation. So this is unoccupied, this is unoccupied, this is unoccupied, this is this one, sorry not this one, this is occupied, this one, this is again unoccupied cell, this is also unoccupied cell, unoccupied cell. So we will find out the delta ij for all the unoccupied cell. So delta 11 is an unoccupied cell, so is equal to C11 minus U1 plus V1. So C11 is 5 minus 0 plus 1, 4. Similarly, we have obtained for all the unoccupied cells delta ij using the relationship. Now you can see from the table the opportunity cost for all the unoccupied cell is shown by this box. The values shown in box is the opportunity cost for the unoccupied cell. So for this unoccupied cell it is 4, for this it is 4, for this it is 3, then for this unoccupied cell it is 0, for this it is minus 2, for this it is 0, for this it is 7, for this it is 0, for this it is 3, for this it is 2, for this it is minus 1, and for this it is minus 3. So as per the rules, if any of the unoccupied cell possesses the negative value, if any of the unoccupied cell opportunity cost possesses negative value, then we cannot get an optimal solution. So we will have to first of all obtain all the values either positive or 0, but here we are having the opportunity cost as minus 3, minus 1 and Okay, there are two values with minus opportunity cost, -2, -1 and -3. This is -2, this is -1 and -3. So now we will have to draw the loop. So highest negative value among that -1, -2 and -3 is in the cell 4-3. You can see over here, cell 4-3. This is the highest negative value in terms of digit. So lowest negative transfer is epsilon, and hence the transfer does not alter the figures except changing the position of alpha to dummy C. All the positions are independent. So now we will draw the loop from this point and we will see what happens. So this is the point where we had highest negative value, that was -3. This is our starting point, so we will put plus sign over there. Now we will have to draw in such a way that it becomes a closed loop. So you can draw the closed loop here. From this point you can go towards this 50. Now you can take right hand turn only from the occupied cell. So what happens now if there is an exchange of allocations? So from here I have gone with the vertical line upward, then I can take right hand turn towards here to this 30 occupied cell. Then again I can take right hand turn from 30 because it is an occupied cell. I have bypassed this and I have reached this epsilon. Now again I will draw the horizontal line, and I have bypassed this 30 and I can reach the starting point. So this is the closed loop that we had formed now. So let us see that closed loop. This is this, plus we had moved to 50. Then with the right hand turn we can only take right hand turn from the occupied cell. So it is an horizontal line. Again to the occupied cell we had bypassed this 50 value and we had drawn the vertical line till epsilon. So from epsilon we can again, there is an occupied cell, so again we can take an right hand turn. We had bypassed this 30 and again I have reached the starting point. So here it was plus, starting point will have plus value, then we can change, alternate signs will be placed. So this is plus, this is minus, this is plus. The cell which you have bypassed, there is no need to put any sign because that is not considered, we had already bypassed. So this was plus, so this was altered sign, that is minus, then this is plus, this is minus, as it is. So now you can see here there is a change in the allocation. Here now lowest negative transfer is epsilon, and hence the transfer does not alter the final figure except changing the position of alpha to dummy C. So we had an allocation of epsilon initially, it was over here, dummy and E column, dummy row and E column. Now we are transferring with to dummy to epsilon to dummy and C column with the help of this loop. Now from here epsilon, it is because among the closed loop we will add or subtract the lowest allocation. So from the loop 50, 30 and epsilon, the lowest allocation is epsilon. Epsilon is almost 0, negligible, its value will not affect the final result. So smallest allocation among the loop among the closed loop 30, 50 and epsilon is epsilon. So epsilon will be added over here. From here epsilon will be subtracted. Here also epsilon will be added. 50 will remain as it is, and epsilon is subtracted from epsilon. So this cell now becomes 0. There is no allocation. It becomes an unoccupied cell. So 50 as it is, 30 as it is, 40, 40. Here it is an epsilon. Now because this epsilon moves over here, it is added over here, that is this is 30. Now this becomes 0. So now the degeneracy is removed. Now you can see the number of allocations: 1, 2, 3, 4, 5, 6, 7 and 8. So again checking with the help of formula m plus n minus 1, there are 4 rows and 5 columns minus 1. So 4 plus 5, 9 minus 1, 8. So we have now total allocation of 1, 2, 3, 4, 5, 6, 7, 8. So now degeneracy is removed using Modi method to check the optimality. So again we had checked with the help of Modi method, and we had obtained now these values of u1, u2, u3 and u4 with the help of this relationship of occupied cell. So this all the values we have put in this table of v1, v2, v3, v4, v5 and u1, u2, u3, u4. Now calculating again the opportunity cost for all the unoccupied cell using the relationship delta ij is equal to Cij minus ui plus vj. So for the unoccupied cell we had find out the opportunity cost, and that is shown in the box, in rectangular box. These all are the values of opportunity cost for unoccupied cell. This is allocation of 50, 30, 40, 10, 40, 50, epsilon, it is negligible, and this is 30. So all the values we have substituted, and we can see that all the unoccupied cell now possesses either 0 value or all the values are positive. Plus 1, plus 4, 0, plus 3, 1, 3, 4, 0, 0, 2, 2, 3. So now we can say that we have reached the optimal solution for the given problem. So as all the opportunity cost of the unoccupied cell is either 0 or positive, so optimal solution is reached. So now finding the total transportation cost. From this table, wherever we had an allocation, we will multiply these values with the number of units to be transported. This values shown in the circle is Xij, that stands for number of units to be transported, and the values other than the circle, this 6 is the unit transportation cost. So multiplying those allocation values, so we can get 6 into 50 plus 3 into 30 plus 4 into 40 plus 6 into 10 plus 4 into 40 plus 3 into 50 plus 0 into epsilon plus 0 into 30. So if you make an addition of all those allocations, you can find the total transportation cost, and that is 920. So I hope this would have cleared you what is degeneracy in transportation problem. Thank you.